So why do we want to know the shape of a molecule? How does it help us to know that a certain molecule is trigonoplanar versus trigonopyramidal? Well, this is going to help us figure out its polarity. So far we've figured out used electronegativity values to determine whether a covalent bond is polar or nonpolar. But what we were looking at is just the bond itself, not the molecule as a whole. So we figured out that one specific bond based off the electronegativity values. So we subtracted them and then used this chart here to figure out if it was nonpolar or polar. Which range did it fit in? Well, now what we're going to do with the structures, the geometry, we're going to use it to determine whether the entire molecule is polar or nonpolar. Because you can actually have polar bonds on a molecule where individual bonds are polar, yet the molecule itself is nonpolar. So the geometry is going to help us figure that out. So one way to figure this out is by calculating the net dipole. So what a dipole is, it's a separation of charges between two covalently bonded atoms. We represent it by vectors, and the vectors that I'm speaking of are the arrows in the picture below. So usually what we have is the arrow points towards the more electronegative atom. So in this case of carbon dioxide molecule that we have below, oxygen is the more electronegative atom, so we would draw a vector pointing, or an arrow pointing toward the oxygen. Well, that's just one of the bonds. There's another bond going from carbon to another oxygen. So we would then draw another vector pointing towards the oxygen because oxygen is more electronegative than carbon. So in the case of this carbon dioxide molecule, what happens is those vectors cancel each other out because we have one going to the right and one of equal magnitude going to the left, making them cancel. So when the vectors cancel, we get no net dipole, 0. Okay? So if we have no net dipole, that means the molecule itself is nonpolar. So even if that carbon-oxygen bond is polar, the molecule as a whole, since the arrows cancel, is nonpolar. So let's look at when the arrows don't cancel. So in the example of water. So water, H2O, is a polar compound. So how do we figure that out? Well, we can figure it out one way by using this net dipole method. So between hydrogen and oxygen, so looking at just one of those bonds, oxygen is more electronegative than hydrogen. So once again, I'm drawing an arrow pointing towards the oxygen. Well, I need to do it to all bonds present, so I do it again to the other hydrogen-oxygen bond. So now, notice since this molecule is bent, because when we draw the Lewis structure, we go through all the steps to figure out the shape, we'll see that that oxygen atom actually has 2 lone pairs on it. So that oxygen will have a total of 4 things around it, 2 of those things atoms, 2 of those things lone pairs, giving it a bent shape. So since it has a bent shape, now the vectors don't cancel each other out. So imagine picking up these arrows and adding them from head to tail. So I'm going to take this first arrow that goes in this direction. Okay, so that's this arrow here. Then I'm going to pick up the other arrow and add it to this one. And you always add arrows or vectors head to tail. So that arrow is going in this direction. So notice they're not canceling each other out. We have a total net dipole from the very tail of the arrows to the head of the arrows. So if we have a dipole, if the arrows don't cancel each other out, that tells us it is a polar molecule. Another way to figure out if the molecules are polar or nonpolar is by applying the rules on the following slides. So for this first slide, we're talking about nonpolar molecules. So you can actually apply these rules to the Lewis structure. You don't even have to know the molecular shape of it. So the first rule says molecules that have no lone pair on the central atom and all terminal atoms are the same, it's going to be nonpolar. So there's 2 examples shown here. So I have carbon tetrachloride, so carbon with 4 chlorines around it. So it is a molecule, and it has no lone pairs on the central atom, no lone pairs on the carbon. And all the terminal atoms, so all the atoms that's attached to it, are the same. They're all chlorines. So that means this is nonpolar. I don't even have to draw my vectors. Just with those rules, I can tell you it's nonpolar. However, if you have a central atom with no lone pairs, but the terminal atoms are not the same, so if I replace one of these chlorines with a hydrogen now, looking over here, I've now changed the game. It's now going to be polar. So you need to make sure it fits both. No lone pairs on the central atom and all terminal atoms the same. Let's look at the next rule. So molecules that are made up of only carbon and hydrogen are always going to be nonpolar. So what that means is if you only have carbon and hydrogen present, no other elements, so if you throw in an oxygen or a nitrogen or anything else, this doesn't apply anymore. But if it's just hydrogen and carbon, it's going to be a nonpolar molecule. It doesn't matter if you have 52 carbons and 87 hydrogens, it's still going to be nonpolar. This is very helpful because a lot of hydrocarbons, that's what compounds with carbon and hydrogen only are called, hydrocarbons. With hydrocarbons, they often get to be very, very long chains. So you can have extremely large molecules. And in that case, it's going to be really hard to try to draw the shape, figure out all the vectors. So this one's very useful. Saves you a lot of time. Last but not least, diatomic molecules with two atoms of the same element. So if you have a hydrogen and hydrogen attached to each other, their electronegativities cancel each other out, so it's going to be nonpolar. Same goes with any of the other diatomics. There are actually 7 elements on the periodic table that exist as diatomics in nature. Hydrogen, oxygen, chlorine, nitrogen, and the rest of the halogens as well. So now let's look at some rules we can apply to figure out if a molecule is polar. So molecules that have one lone pair on the central atom, or when all terminal atoms are not the same. So we've looked at this second example already. Okay, this was the no lone pair example. When we replaced the chlorine with a hydrogen, we said, okay, now it's polar. But the first part of this rule says if there's a lone pair. So no matter what, if you see a lone pair on a central atom, it's going to be polar. So you don't even have to know the shape yet. You can just have the Lewis structure and see, hey, there's a lone pair, it's polar. The next rule says molecules with more than one lone pair on the central atom are usually polar. So most of the time, 90% of the time, but there are some exceptions. Water is not an exception. Water is a polar molecule. You can see in the example, there are 2 lone pairs on that central atom of oxygen, making it polar. And you couldn't see it, so going back over to this nitrogen trihydride example, it might be hard to see, but there is a lone pair on the nitrogen. So that's why nitrogen is polar. There's a lone pair on the central atom, causing it to be a trigonal pyramid. Couldn't think of the name. All right. So taking this a step further, because we're always adding on. Once we know the polarity, this is going to help us figure out some other pieces of information. It can help us with determining solubility, melting points, and boiling points. So there's 2 types of forces occurring within molecules. So there's intramolecular forces, and these are attractive forces within the molecule itself. So the chemical bonds that determine the shape, all of that. Okay, we're not going to be focusing on intramolecular, what's going on within the molecule itself. What we're going to focus on is intermolecular, so ER, intermolecular. Now these are attractive forces between 2 different molecules. So for instance, say you had a water molecule and a sodium chloride molecule. We would be looking at the intermolecular forces, so the forces between that sodium chloride and that water molecule. Why are we focusing on this? Because intermolecular forces determine solubility, melting points, and boiling points. So we're going to be able to, knowing the structure and the shape and the polarities of molecules, we're going to be able to predict if they're going to be soluble in one another. We're going to be able to predict which one's going to have the higher melting point or boiling point. A general rule for melting points and boiling points is that polar compounds will be higher than nonpolar. And actually, ionic will be the highest. So it goes ionic, highest melting points, polar in the middle, and then nonpolar having the lowest. Melting point and boiling points depend mainly on three things. The first thing being polarity. And this is the most important. This is the one that's going to affect it the most. So the polar compounds, polar covalent compounds, will be higher than nonpolar. So looking at this example here, we have carbon dioxide versus water. Okay, so carbon dioxide, we saw this in a couple examples actually, and we saw that it was a linear molecule and that it was nonpolar. So I'm going to write NP for nonpolar. Now water, we said, was bent because it had two lone pairs on the central atom being oxygen, and so it was a polar molecule. So if I know the polarities, carbon dioxide being nonpolar and water being polar, I can figure out just from that which one's going to have a higher melting point and boiling point. The polar one will. So that means water is going to have a higher melting point and boiling point than carbon dioxide. And we can actually see this is true because at room temperature, water is a liquid and carbon dioxide is a gas. So if it's a gas, that means that its boiling point is very, very, very low. Number two, the intermolecular attractive forces. So these were the forces between the molecules. Now the intermolecular forces depend on polarity. So they both fall into the same category. So if we know the polarity, we know what the intermolecular forces are. So it's not something we necessarily calculate, we just use it to figure out polarity. Last but not least, molecular mass. Now we're only going to apply molecular mass if the polarities are the same. So what I mean by that, if we have two nonpolar compounds and we're trying to figure out which one has the higher melting point or boiling point, then we would resort to calculating the molecular mass. So we'll learn to calculate molecular mass in the next chapter. The larger the mass, the higher the melting point or boiling point. And here is that chart I was talking about on the previous slide. Remember that ionic has the highest. So if you are looking at two compounds and one of them is ionic and the other is covalent, the ionic one will have the higher melting point and boiling point. If you're looking at two covalent compounds, that's when you need to figure out their polarities and use that to predict which will have the higher. So now we've looked at melting point, boiling point, let's look at solubility. So solubility is the maximum amount of substance that can dissolve in a given amount of liquid at a certain temperature. So we actually tested solubilities in lab 4 when we were seeing our unknowns solubility in water. So did they dissolve in each other or not? So how are we going to use polarities to figure this out? Well, we're going to use the general rule that like dissolves like. What that means is polar things will dissolve in polar solvents. Nonpolar compounds will dissolve in nonpolar solvents. So if we're trying to predict if two things are going to be soluble in one another, we look at their polarities. If they are both polar, then yes, they are soluble. If they are both nonpolar, then yes, they are soluble. If one is polar and one is nonpolar, then no, they will not be soluble in one another. Let's use the example from the previous slide. We looked at carbon dioxide and water. Carbon dioxide we said was nonpolar. Water we said was polar. So one's polar, one's nonpolar. So are they going to be soluble in one another? No, they won't, and they're not. So carbon dioxide, think of carbonated beverages, soda. Okay, that carbon dioxide is not dissolved in the soda. That's why when you open a can of soda, you hear that sound, because as soon as you open it, what's happening is those carbon dioxide bubbles are trying to escape because they're not soluble in the liquid. That's why soda cans need to be pressurized, because they're trying to force the carbon dioxide into that liquid. If you leave the can open, eventually all the carbon dioxide is going to escape, leaving you with a flat soda. They are not soluble in one another because they have different polarities.